They regulated power without electronics in the 1800s, and the system remained stable. Imagine a power system supplying constant power to hundreds of machines simultaneously, automatically adjusting to load variations, maintaining stable speed regardless of fluctuating demand. All this without a single electronic component. No digital sensors, no microprocessors, no control circuit, just pure mechanical physics and design ingenuity. This is not technological speculation. It is exactly how factories, power plants, and infrastructure systems operated during the 19th century. While modern systems rely on sophisticated electronics to maintain stability, Victorian engineers developed purely mechanical mechanisms that regulated power with remarkable precision. The question is not whether these systems worked. We know they worked because they operated entire industries for decades. The question is how they achieved stability without the electronic feedback technology that we consider essential today. This roadmap will explore 10 different mechanical regulation mechanisms developed and perfected in the 19th century. Each mechanism solves a specific control challenge, maintaining constant speed under varying load, preventing catastrophic overload, distributing power evenly among multiple points of use, and automatically responding to changes in demand. They all share common principles. They use physical forces to create negative feedback, convert unwanted variations into corrective actions, operate continuously without human intervention, and when well designed, achieve stability that rivals modern electronic systems. We begin with the most fundamental of these mechanisms. If you're fascinated by the idea that 19th century engineers developed purely mechanical automatic control systems that maintained stability without any electronics, leave a like supporting the exploration of engineering solutions that demonstrate that precise control. Doesn't necessarily require digital technology. Subscribe for analyses of working historical mechanisms, not speculation about lost technologies. Turn on notifications so you don't miss investigations of systems that can still be observed operating in industrial museums. If you value an approach that examines principles of physics and engineering rather than making sensationalist claims, click the Hype R button supporting content that explains how things really work. The first regulatory mechanism begins now. Centrifugal ball governor controlled the speed of steam engines automatically. The centrifugal governor, also known as Watt's governor, after being perfected by James Watt in 1788, is the most iconic automatic control mechanism of the industrial age. How it works? Two metal spheres mounted on articulated arms, connected to a vertical shaft that rotates with the machine. When the speed increases, centrifugal force pushes the spheres outward. This upward movement of the spheres connects, via levers, to a valve that reduces steam flow to the cylinder. Speed decreases, spheres descend, valve opens wider, speed increases again. The system creates a purely mechanical negative feedback loop. Speed deviation in either direction generates an automatic corrective response in the opposite direction. The elegance lies in its simplicity. Just gravity, centrifugal force, and levers. No sensors, no processing, no external power source for control. The very movement that needs to be controlled provides the energy for the control mechanism. Practical implementation required careful adjustment. The sensitivity of the governor depended on the mass of the spheres, the length of the arms, and the geometry of the levers. Well-designed governors maintain speed within about 2% of the target speed, even with load variations of 50%. This level of accuracy was adequate for most industrial applications. The governor on the 1876 Corliss steam engine, installed at the Philadelphia Centennial Exposition, controlled a 1,400 horsepower machine that powered all the machines at the Industrial Exposition. The centrifugal governor maintained a stable speed while hundreds of machines were switched on and off randomly throughout the day. Engineers observed that the speed rarely varied more than 30 revolutions around the target of 120 revolutions, an accuracy of 2.5% under highly variable conditions. This same principle was applied in thousands of industrial installations. Textile mills used governors to maintain consistent speed of looms and spinning machines. Municipal pumping stations used them to control water pumps. Early electric generators used centrifugal governors to maintain stable frequency. The governor remained standard technology for speed control until the mid-20th century. Some applications still use variants of the centrifugal governor today, particularly in small hydroelectric systems where simplicity and reliability are more important than extreme precision. Fundamental physics is immutable. Centrifugal force always increases with speed, creating an inherently stable feedback mechanism. Weighted safety valves automatically released excess pressure without fail. Second regulation mechanism, weight-loaded pressure safety valves. Problem: steam boilers operate under high pressure. If the pressure exceeds a safe limit, the boiler can rupture catastrophically. Solution: a valve that opens automatically when the pressure exceeds a predetermined limit. Basic design: a metal disc sits on an opening in the boiler. A known weight presses the disc against the opening. When the steam pressure exceeds the weight force, the disc lifts, steam escapes, the pressure decreases, and the disc returns to its seat. Completely passive, it requires no detection, decision, or human action. Physics ensures operation. The weight force is constant and known. The disc area is fixed. The pressure at which the valve opens is determined by the simple equation: weight force divided by the disc area. To adjust the opening pressure, add or remove weight. To increase accuracy, use a lever multiplying the weight force. Implementation in 19th century industrial boilers was ubiquitous. Safety codes required multiple independent safety valves in each boiler. The primary valve was set to normal operating pressure. The secondary valve was set 10% above. The tertiary valve was set 20% above. If the primary control system failed and pressure began to rise, the first safety valve would open, releasing enough steam to prevent further increase. If this failed, the second valve would open. The multiple valve system created redundancy that made catastrophic failure extremely unlikely. Inspection of safety valves was a regular ritual in boiler operation. Inspectors checked that weights were correct, that valves were not obstructed, and that seats were sealing properly. Periodic testing consisted of manually lifting the valve using a test lever, verifying that steam escaped freely. The reliability of well-maintained safety valves was exceptional. Records from industrial insurance companies from the late 19th century show that boiler explosions were almost always caused by tampered safety valves, operators adding extra weight to allow higher pressure, or tying valves closed. When valves operated as designed, failures were extremely rare. The principle of the pressure safety valve remains in use today in virtually every pressurized system. Modern boilers, pressure vessels, hydraulic systems all use pressure relief valves operating on exactly the same physical principle as 19th century valves. Electronics may have been added for monitoring, but the ultimate safety mechanism remains purely mechanical because it is inherently reliable. Speed governors in elevators prevented free fall. Through centrifugal force third mechanism, elevator safety governor. Specific challenge: a cable-suspended elevator can fall if the cable breaks. Passengers inside would experience a potentially fatal free fall. Solution developed by Elisha Otis in 1852, a mechanical governor that detects excessive speed and automatically activates brakes. Operation: a pulley with weights mounted on the periphery rotates as the elevator moves. At normal speed, the weights remain close to the center. If the cable breaks and the elevator begins to fall, the descent speed increases rapidly. Centrifugal force pushes the weights outward. When they reach their limit position, they activate levers that release powerful springs. Springs push brake shoes against side rails, locking the elevator in position. The entire mechanism is purely mechanical. It requires no external detection or power source. The dangerous condition itself, excessive speed, provides the force that activates the safety system. Otis's first public demonstration of this mechanism in 1854 at the Crystal Palace Exposition in New York was dramatic. Otis climbed onto an elevator platform and ordered an assistant to cut the supporting cable. The platform dropped a few centimeters before the safety brakes engaged with a loud metallic noise, stopping the fall completely. The audience was silent for a moment, then applauded. This demonstration transformed public perception of elevators from dangerous to safe, enabling the construction of tall buildings. The reliability of the Otis governor was such that it became a worldwide standard. Variations of the original design are still used in modern elevators. Some contemporary elevators add electronic sensors and control systems, but the mechanical governor remains the ultimate safety system because it is fail-safe. It fails in the safe position. If any component breaks, the result is brake activation, not failure to engage. Technology museums often have 19th century Otis governors on display. Mechanisms 150 years old can still be operated manually, demonstrating principle. The simplicity of the design, just weights, springs, and levers, ensures durability. There are no components that degrade or require periodic calibration. Once properly adjusted, the governor operates indefinitely. Water regulators and turbines adjusted power output in response to load changes. Fourth mechanism, Automatic gate regulator in hydraulic turbines. Problem. A. Hydroelectric turbine connected to an electric generator must maintain a constant speed for a stable electrical frequency, but electrical load varies constantly as users turn equipment on and off. Solution. A regulator that adjusts the flow of water through the turbine in response to changes in speed. Typical implementation used the principle of the centrifugal governor adapted for hydraulic control. A centrifugal governor mounted on the turbine shaft detected changes in speed. Movement of the governor's spheres controlled a pilot valve in the hydraulic system. The pilot valve directed pressurized oil to a large piston that opened or closed the turbine's water gates. The leverage system created amplification. A small movement of the governor caused a large movement of the gates. The critical aspect was stability. A poorly designed system would oscillate, gates opening too much, then closing too much, creating speed variations instead of eliminating them. 19th century engineers discovered that adding damping to the hydraulic system prevented oscillation. A dashpot, a cylinder with a piston moving through viscous oil, created resistance proportional to the speed of movement. This prevented abrupt changes while still allowing for an adequate response to real disturbances. The Niagara Falls Hydroelectric Plant, commissioned in 1895, used automatic governors developed by Westinghouse engineers. Each of the three 5,000 horsepower turbines had a governor that maintained a speed of 25 revolutions per minute with a variation of less than plus or minus 0.5%, even when load varied from 0 to 100% of capacity. This precision was essential because generators supplied electrical power to Buffalo, 26 kilometers away. Frequency variations would cause problems in electric motors and lighting. The durability of these governors was remarkable. Some of the original Niagara governors operated with regular maintenance until the 1960s, 70 years of continuous service. Maintenance consisted mainly of replacing hydraulic oil and occasionally repairing seals. The main mechanical components, centrifugal governor, valves, pistons, were manufactured with precise tolerances and durable materials that resisted wear. Principles developed in these early hydraulic governors form the basis of modern turbine control systems. Electronics have been added for monitoring and fine-tuning, but many hydroelectric plants still use mechanical hydraulic regulators as the primary control system because they are robust and reliable. Mechanical current limiters protected generators through automatic disconnection. Fifth mechanism, electromechanical overcurrent circuit breaker. Challenge. Electric generators and motors can be damaged by excessive current caused by short circuits or overloads. Electronic protection did not exist in the 19th century. Solution. A device that detects excessive current through a magnetic effect and disconnects the circuit mechanically. Basic operation. Electric current passing through a coil creates a magnetic field proportional to the current. In normal operation, the magnetic field is weak. When the current exceeds a safe limit, the magnetic field becomes strong enough to attract the iron armature. The moving armature releases a mechanical latch that allows a spring to open electrical contacts, interrupting the current flow. The system is completely passive until the moment of activation. No external power source is required. The excessive current itself, which poses a danger, provides the energy to activate the protection. Once opened, the circuit breaker must be manually reset, forcing an investigation into the cause of the overcurrent before restoring power. Early electromechanical circuit breakers were developed for electric lighting systems and electric trams in the 1880s. The design evolved rapidly as engineers better understood the behavior of electrical circuits under fault. Conditions. A circuit breaker needed not only to open a circuit, but also to extinguish the electric arc that forms when contacts separate under load. An arc can continue to conduct current even with contacts separated. Solutions included arc extinguishing chambers where contacts opened in an environment that cooled and lengthened the arc until it extinguished. More sophisticated circuit breakers used trip coils for both overcurrent and thermal overload. A bimetallic element heated up with direct current. Prolonged moderate overload caused gradual heating of the bimetal until it bent sufficiently to trigger mechanical opening. A sudden short circuit caused instantaneous tripping through magnetic attraction. Two independent protection mechanisms in the same device. General Electric produced molded case circuit breakers from the 1930s that incorporated principles developed in 19th century devices. These circuit breakers operated without electronic components, using only magnetism, bimetals, and spring mechanisms. Millions were installed and operated reliably for decades. Modern residential circuit breakers still use the same fundamental principles: magnetic overcurrent detection, bimetallic thermal protection, mechanical contact disconnection. Electronics have been added to some high-voltage circuit breakers for advanced capabilities, but basic protection remains electromechanical because it is simple and reliable. Hydraulic accumulators stabilize pressure through constant mass and gravity. Sixth mechanism, hydraulic pressure regulation via gravitational accumulator. Urban hydraulic power systems, such as the one in London operated from 1884 to 1977, provided hydraulic pressure to operate elevators, cranes, and other machines. Demand varied constantly, multiple machines switching on and off randomly. Pumps could provide average flow, but could not respond instantly to peak demand. Solution: an accumulator that stores energy and simultaneously regulates pressure. Design: a large vertical cylinder with a massive piston sliding inside. The weight of the piston, typically 100 to 300 tons, creates constant pressure in the hydraulic fluid below, independent of volume. When pumps supply more fluid than consumption, the piston rises, storing energy. When consumption exceeds pumping, the piston descends, supplying additional fluid. Throughout this process, pressure remains essentially constant because it is determined only by the weight of the piston divided by the area of the piston. Regulation is perfect within physical limits. Pressure does not vary with demand. There is no oscillation, no overshoot, no need for adjustment. The physics of gravity ensured operation. The London hydraulic power system had accumulators at each pumping station. The largest accumulator had a 200-ton piston, a diameter of 3 meters, and a stroke of 7 meters. This provided approximately 500 cubic meters of fluid under a constant pressure of 700 psi. This capacity was sufficient to absorb variations in demand for periods of 10 to 15 minutes, adequate time for additional pumps to be started if necessary. Operators monitored the piston position. If the piston was high, demand was low, and pumps could be switched off. If the piston was low, demand exceeded pumping capacity, and additional pumps were started. But at no time did the pressure vary significantly. Users of the system received stable pressure independent of load fluctuations. The durability of the accumulators was exceptional. Cylinders manufactured in the 1880s operated until the 1970s. Maintenance consisted of lubricating seals and occasionally repairing minor leaks. The piston itself, being a solid mass of iron, never needed replacement. Compare this to modern constant pressure systems that use electronic sensors, controllers, and variable speed pumps. Gravity accumulators achieve the same result: constant pressure under variable load with components that last for generations. Automatic brakes on trains applied spring pressure when air pressure failed. Seventh mechanism, automatic air brakes for trains, developed by George Westinghouse in 1869. Critical problem: trains with multiple cars need brakes that apply simultaneously to all cars. If rear cars do not brake when the locomotive brakes, they will collide with front cars. More importantly, if the coupling between cars breaks, separate cars must brake automatically. Ingenious. Solution: a system that applies brakes when air pressure is lost, not when pressure is applied. Design: each car has a brake cylinder with a compressed spring on one side and compressed air on the other. In normal operation, air pressure compresses the spring, keeping the brakes released. An air line connects all cars. When the driver applies the brakes, it reduces the pressure in the air line. Springs in all cars expand simultaneously, applying brakes. If the coupling breaks, the air line brakes. The pressure drops to zero, and the springs apply brakes completely to both sections of the train. The system is fail-safe. It fails in the safe position. Loss of pressure for any reason results in braking, not a loss of braking capacity. This contrasts with previous systems where braking depended on the application of pressure or force. If the system failed, the brakes did not function. With the Westinghouse system, failure results in braking. Practical implementation required a triple valve in each car, a complex mechanical device that controlled the gradual application and release of brakes in response to changes in mainline pressure. When the engineer reduced mainline pressure, the triple valve detected the pressure change and directed air from a local reservoir to the brake cylinder. When pressure was restored, the valve redirected flow, releasing the brakes. All this control was purely mechanical: springs, diaphragms, seat valves. The Westinghouse system became a worldwide standard for trains. It saved countless lives by preventing collisions caused by brake failure. Variations of the system are still used in modern trains. Some contemporary systems have added electronic controls for precise modulation, but the fundamental principle remains. Brakes apply when pressure fails, ensuring safety even in fail-safe conditions. Bimetallic thermostats, controlled temperature through the differential expansion of metals. Eighth mechanism, bimetallic thermostat for temperature control. Need to maintain a constant temperature in incubators, greenhouses, heaters, or industrial processes without constant monitoring. Solution, a device that automatically switches a heat source on or off based on temperature. Physical principle, different metals expand at different rates when heated. Bimetallic strip, two strips of metal with different expansion coefficients bonded together. Bends when the temperature changes. One side expands more than the other, causing curvature. This curvature can trigger an electrical switch or mechanical valve. Implementation in a typical thermostat. Bimetallic strip in the shape of a spiral or disc. As the temperature increases, the spiral coils or the disc deforms. When it reaches the target temperature, movement is sufficient to open electrical contacts or close a valve, switching off the heat source. As the environment cools, the bimetal returns to its original shape, switching heating back on. Oscillation around the high target temperature is minimized by careful design of the switching mechanism. Intentional hysteresis, the difference between the on and off temperatures, prevents rapid cycling. Bimetallic thermostats were developed in the 1830s, initially for regulating dampers in furnaces. Their application expanded as electricity became available. Electric thermostats for residential heating became common in the 1880s. Honeywell began mass production of residential thermostats in 1906. The basic design remained unchanged for decades. Bimetallic element, temperature adjustment mechanism, electrical contacts. The accuracy of well-designed bimetallic thermostats was astonishing. Devices could maintain temperatures within plus or minus 1 degree Celsius of the target. For many applications, including residential comfort and non-critical industrial processes, this accuracy was perfectly adequate. Durability was excellent. Mechanical thermostats installed in the 1920s often operated until they were replaced by digital units in the 1990s. 70 years of service. Maintenance was virtually non-existent beyond occasional cleaning of contacts. Bimetallic thermostats are still manufactured and used today, particularly in applications where simplicity and reliability are more important than extreme precision. Water heaters, irons, toasters, they all use bimetallic thermostats. The principle remains valid because it is based on a fundamental physical property of materials. Traction. Regulators on locomotives limited force through pressure valves. Ninth mechanism. Traction regulator in steam locomotives. Specific challenge. When starting heavy train movement, traction force must increase gradually. Sudden application of maximum power causes wheels to slip, damaging rails and wasting energy. Solution. Regulating valve that allows the engineer to increase power progressively, with mechanical limiters preventing excessive application. Implementation, butterfly valve or guillotine valve in the steam duct between the boiler and cylinder. The engineer controlled the valve via a ratchet lever. Each increment of the lever opened the valve slightly more. A return spring ensured that if the lever was released, the valve would close automatically. The leverage system was designed to provide fine control in low opening positions where precision was most important and faster movement in high opening positions. Additional safety mechanism, pressure limiter that prevented full valve opening if boiler pressure was low. This prevented the engineer from trying to extract more power than the boiler could supply, which would result in rapid pressure loss and the need to stop to recover steam. The limiter used a pressure-sensitive diaphragm mechanically connected to the valve mechanism. Low pressure blocked further lever movement. Advanced locomotives also had pressure indicators visible to the engineer, but mechanical protection ensured safe operation even if the indicator failed or was ignored. Engineer training emphasized the correct use of the governor. Operating manuals specified opening sequences for different load and gradient conditions. An experienced engineer could start a heavy train smoothly, increasing power precisely as speed increased, avoiding wheel slippage. Skill in using the governor was a mark of a competent engineer. Preservation of historic steam locomotives keeps these governors functional. Enthusiasts who operate preserved locomotives learn original control techniques. Experienced operators report that well-maintained governors provide surprisingly precise control, allowing smooth power modulation across the full operating range. Mechanical feedback devices, coordinated complex system without processing 10th and final mechanism, complex mechanical linkage systems for coordinating multiple elements. Example, aircraft radial engine control system developed in the 1920s, 1930s, heir to 19th century principle. Challenge. Multi-cylinder radial engine requires precise coordination of multiple valves and controls, responding simultaneously to a single pilot input. Solution, lever, cam, and linkage system that converts single control movement into multiple coordinated component movements. The air-fuel mixture control system used linkage that simultaneously adjusted throttle valve, fuel valve, and ignition timing based on a single power lever position. As the pilot moved the lever to increase power, the linkage opened the air throttle, increased fuel flow proportionally, and advanced ignition timing. Proportions were determined by carefully designed linkage geometry. A cam with a specific profile converted linear input movement into precise rotations and angular displacements of multiple outputs. Mechanical feedback was built into the system. Fuel valve position influenced linkage that controlled the air throttle through mechanical connection. This created a coupling that maintained correct proportions even if an individual component encountered resistance. If a fuel valve partially stuck, the linkage would limit throttle opening correspondingly, preventing operation with an incorrect mixture. The complexity of linkages in advanced mechanical systems was remarkable. A typical aircraft engine control mechanism could have 30 to 50 linkage elements: levers, connecting rods, pivots, cams, springs. Each element needed to be manufactured to precise tolerances and assembled correctly. But once adjusted, the system operated reliably for hundreds of hours without needing recalibration. Maintenance consisted of lubrication and checking for wear on pivots. The transition to electronic controls in aviation occurred gradually. Early fly-by-wire systems in the 1970s still retained mechanical backups. Only in more recent aircraft are controls purely electronic. But even today, aircraft certification requires demonstration that control systems remain operable under multiple failures. Principles of redundancy and fail-safe developed in 19th century mechanical systems inform the design of modern electronic systems. If these 10 purely mechanical regulation mechanisms from the 19th century demonstrated that precise control and stability of complex systems were achievable decades before electronics existed, leave alike supporting the exploration of engineering principles that transcend specific technology. Subscribe for analyses of historical systems that reveal elegant solutions based on fundamental physics. Click on the video appearing on the screen to continue exploring how engineers solved complex problems with limited tools, but a deep understanding of mechanical principles. Thank you very much for taking the time to understand that regulation and automatic control did not begin with computers, but with the ingenious application of physical forces and feedback mechanisms. See you in the next exploration of verifiable historical engineering.